All right, we'll just go ahead and start here. I'll check the audio here in a moment, but last time we left off talking about Dijkstra's algorithm. Dijkstra's algorithm, the idea here is that you are given a single source vertex S in a weighted graph. It can work on an unweighted graph. It can work on a directed, weighted, unweighted graph. It'll work on any type of graph. And it finds the shortest path from that source vertex to all other vertices in the graph, right? And the idea here is that you start at S and you start exploring the neighborhoods. In fact, it's almost virtually exactly the same as Prim's algorithm, except that the idea is that you don't you still make locally greedy choices, but you're not trying to minimize the overall tree. You're trying to minimize the path with respect to wherever you start with. And so you always select the least weighted path vertex instead of the least weighted edge. You consider the entire path up to that point. And then you explore the vertex's neighborhood. If you find a lesser path, then you update that. Like, oh, I can now get to X. If I go from here, I can get to X. Whereas the path that I found before was much larger as far as weight goes. And so I'll update it because this is a better path, right? And then you always keep track of a predecessor vertex. And of course the current weight, because the predecessor vertex is there because you want to know how do I actually build the path after I'm done, right? Each iteration fixes a vertex or path into the tree, right? Again, it's not a minimum spanning tree, but it is a minimum weighted path tree, okay? Let's come back over here and just really quickly review what we did last time on this particular graph, right? What we did is we started out at E, and then we initialized everything over here in this heap as you observed last time, because every iteration we take out the least element, right? We started at E, and we could see immediately these three outgoing vertices. And so from an infinite weight, we can now get to B at a weight of 5. We can now get to D at a weight of 5. We can now get to G at a weight of 20. Ultimately, this edge was not taken, though, because eventually we found another path going from D to G with a weight of 5 plus 10. 15 is better than 20. Right? Along the way, we kept track of the predecessor vertex and the weight that got us there, so that eventually when you go from E to G here, right, where is it? G right here, then it tells you that you go to D first. The most complex one here was probably I, right? And you can get to I at a weight of 20. Well, how did we get there? Well, first of all, we came from G. So backtracking here, we came from G. Well, how did we get to G? Right? Well, that's this one right here. We got to G from D, so backtracking yet again to D. Well, how did we get to D? We got there from I. So there is how you end up building a path, a shortest length path from E all the way over here to I at a cost of 5, 15, 20 total. Right? That's how it worked. Let's go ahead and write out the pseudocode for doing this. And like you observed last time, let me just check one really quick here, making sure that the audio is working. Yep, it is. All right, so you observed last time that you probably want to use some sort of a priority queue or heap because you're putting these triples into a data structure and you're always wanting to pull the highest priority, the least weight out next. Okay? So here's dijkstras. And there was, did we ever reach a consensus on what the pronunciation of it is? I've been saying dijkstras for years. The Witcher, you said? The Witcher has somebody named Dijkstra? So in the game, yeah. They say dijkstra? Yeah. Is he in the TV show? How do they say it in the TV show? Okay, all right. Anyway, we won't worry about that. So our input here is going to be a graph, and again, it can be a weighted graph, an unweighted graph, it can be a directed graph, it can be an undirected graph, it doesn't matter. G equals V comma E, and a source vertex, S, which of course is going to be in the vertex set. Now remember, when we looked at this example, there are going to be some vertices that are unreachable, right? We're going to end up with an infinite weight path to actually get to them. And so that's why they're not highlighted in green like the rest of these things. Okay? So it could be that S never actually makes it out of S, right? You can check for that really easily and then stop immediately if you want. Otherwise, our output will be a set of triples basically, the minimum weighted path from d sub v, where you've got, say, where the path is from S to V, right? So this is going to be the distance or the weight, right? And this is going to be the actual path. We won't output the actual path. We'll develop another algorithm after we're done with this together. That given these triples, how do you reconstruct the path, right? So first of all, I'm going to initialize a priority queue, right? So init priority queue, right? There we go. And then, of course, I need to go through and initialize all the variables. So for each v in v, we're going to set up three things. First of all, the distance will end up being infinite, right? Because we haven't seen it yet. The predecessor vertex here will end up being nil, right? Or nothing, right? So infinite weight and no predecessor. Right? And then finally we enqueue it, q.enqueue those things, right? That triple, say v, and the way that we did it over here is what? Then the predecessor and then the weight. So we'll do it this way. V, the predecessor vertex of v, and then d sub v. So we can see that we're enqueuing three things, a triple. I'm trying to do it more Pythonic for you, right? That you can put in a triple. Now, when you do this, of course, the priority here will be the distance. This is the priority. So when you do this in actual Python, probably that's going to be the first thing that you put in, right? Instead of the third thing that you put in. Okay? And that's my initialization. So init. And then, well, actually, I'm not done with my, that's the initialization for everything else, but what I'm going to do now is I'm going to set up for the source, right? So the distance here will end up being 0, right? Distance from S to S is 0. The predecessor vertex for S will be nil. I guess I don't need to do anything, right? Yeah. Right, that was already done. And then I will enqueue q.enqueue that triple, S, P sub S, and D sub S. So when I did it up here, I really meant except S, right? For all vertices except for S, right? Because you treat that special. This is the init of the source, okay? And then, if you want to, you can keep track of the vertices in the tree, and we'll initialize that to an empty set right there. Okay? Now, here's the main loop. So I'm going to go to the next slide here for the main loop. This is the main loop. Right. So I'm just going to simply do this for I running from 1 up to n. Right? We're doing this n iterations. Because remember the simulation of the algorithm here? What did we end up doing? We ended up with n things in our queue. Each iteration, we took one out and put it over here. How many iterations do we need to go until the queue is empty? N iterations. You could equivalently say, while the queue is not empty, continue, right? So, or while queue is not empty. Okay? I'm going to pull out the thing with the highest priority, or the least weight. So q.dq, or pop, or whatever, right? This is the lowest weighted triple. Okay? And then that becomes part of my tree. So v sub t will end up being v sub t union that node, or that vertex. Now, visually, what that corresponds to is me highlighting these things, right? Once you pull it out, I highlighted it in green here to add it to the tree. And I also highlighted the edge that took us there. Right? So this is the tree that you're building right here, okay? All right, so then what I need to do is I need to look at its neighborhood for each, do I use V here? Yeah, I'll use V, right? In the neighborhood of U, right? Minus V sub t, oops, V sub t, right? So for each node in the neighborhood, that is not already part of the tree, of the Dijkstra tree, what I need to do is I need to look at the weights, right? So for example, before, at some point in the algorithm, I going from E to G had a weight of 20. But after I add D and look at its neighborhood, now I see that I can get to G at a cost of 5 plus 10. Whatever the cost is to get to that edge, that vertex, and then the cost of the additional edge to go to that next edge, is that better than what you've found so far? And if so, then you update it. The way that we're going to write that in pseudocode is simply that it's going to be an update in your priority queue, an update in your heap. All right? So if the distance to U plus the weight of going from U to V is less than the distance that you found so far, let me go ahead and separate that. There we go. Then I will update it, right? So D sub V will then be du plus the weight of going to U to V from U, and then the predecessor vertex of V will then end up being U, right? And then we need to update our queue here to decrease priority of V, P sub V, and D sub V, the new D sub V, right? This is the new value right here, right? New value, or new priority, right? There we go. And that's it for the inner for loop here. Otherwise, that's it for the main loop, right? Now we output all triples. Those triples are going to be V, the predecessor of V, and the distance to V, right? So let's document that on the next page here. V, PV, and DV. These triples are going to be the vertex, the predecessor vertex, and the total weight of the path from S all the way to V. So those are the three things that we're interested in, right? And again, the visualization here, that's what we ended up with, outputting all these things, right? This is the this is a triple, this is a triple, 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 and triple. Okay. And then we do end up with some of these over here that still have an infinite weight because there's no way for you to go from E to H. Okay. Now, before we analyze this algorithm, you tell me. Well, I'm interested in all of the pairs. I'm not just interested in going from E to I. I'm also interested in going from I to E, or from I to C, or something like that. How could we modify Dijkstra's algorithm to do that? Run it once for E, and if you're interested in the rest of them, run it twice, thrice, 4, 5, 6, 7, 8, 9, 10, or in general, n times. If you run this algorithm n times, you will get all pairs, right? Or you can run the Floyd-Varshall algorithm, the Floyd's algorithm that we're going to look at next. But before we do that, let's go ahead and finish up with Dijkstra's. Okay? So on your assignment this Friday, you have a choice. Do you want to do Dijkstra's or do you want to do Floyd's? Either or. Right? And since we're on Wednesday, I'm willing to entertain pushing that back as well because we haven't talked about Floyd's yet. Right? All right. What else do you have on that assignment? Yeah. What else do you have on that assignment? By the way, I completed grading of all the assignment 7s. So those are all done, including the omission of that algorithm. And by the way, if you're not following Piazza, I found the answer, and it's Surabel's algorithm, which is actually a application of Dijkstra's algorithm. You run Dijkstra's once, and then you augment the graph a little bit. It's not as simple as pulling out a path, though. And then you reverse the flow, and then you run Dijkstra's again, and you find two node disjoint paths. And if you have two node disjoint paths between two vertices in an undirected graph, what do you have? A cycle. Right? So I forget. I'd have to look it up, but probably the same as Dijkstra's because that's the main subroutine, right? Which is, yeah, let's talk about that. Right? So let's go over here to, well, this is all just setup, right? This is all initialization. That's not the main show. This is the main show, right? So tell me, what am I doing here? I'm doing some enqueue, I'm doing some dequeuing, right? I am doing some decreased priorities, right? So let's reason this out, the complexity. So first of all, in a heap, in a say binary heap, right? The heap that we're used to here, in a heap of n elements, right? dq is going to be an order log n operation. Right? So if my elementary operation is dequeuing, dq, then one of those things is going to cost me order log n. How many times do I do that? Right here it is, right here. I do it once, twice, thrice. How many times total? N times. You perform n dq operations. Right? So if you're looking at dq operations, in total, what is it going to be? It's going to be order n log n. Good. Okay. That's not the only thing that we're doing with the queue, though, remember? Right? What else are we doing with the queue? We're doing a decreased priority here, right? So you all, I think, did it, right? You corrected Gomer's mistake with a heap, and Gomer had the idea that, right? Correct me if I'm wrong on one of your questions. No? Gomer thought that if you could automatically find the node and decrease the priority, all you had to do was check downwards, and he was wrong. You have to check up or down, right? Because if you're changing the priority and the priority goes up, right, then that means that you need to check up. If the priority goes down, that means that you may need to bubble it down, right? So you corrected Gomer's problem there, right? You can update priority, right? Doing it once, one update operation is going to be, because it's proportional to the height, it's going to be order log n, just like one operation of the enqueue operation. How many total do we do, though? We do up to blank update priority operations. Right? Now, if you just look at the pseudocode, it's not all that apparent, right? You might say, oh, okay, well, we do it maybe n times because we do this for loop n times. And then within that, well, we only do it if we need to, et cetera, et cetera. Think about what you're doing, though. Right? Visually, when are you updating the priority in the worst case? You're looking at for each node, you're looking at the neighborhood of that node. In other words, for each outgoing edge, you're doing, potentially you're doing one update priority operation. Right? Now, if it's an undirected graph and you're oriented both ways, you're doing it once for one orientation and a second time for the second orientation. So we can put an upper bound, a loose upper bound on this as what? Up to 2 times m minus 1. Why? That's interesting. Why minus 1?
You can check the one you came from.
Oh, okay. I think maybe. Well, let's keep it simple, though, because big O, right? Who cares, right? So 2m, right? So in total, how many? Order, that 2 goes away, and we're left with m log n update priority operations. Right, now, 2m update priority operations, but each one of them costs you order log n comparisons. Okay? Likewise, dq is leading to big O of n log n comparisons. So grand total. The number of comparisons using a heap is going to be order m log n plus, right, n log n. Right? Because these are independent. Sometimes you do a DQ operation, sometimes you do an update operation. Now, you can do a little bit more careful analysis and come up with slightly less in an amortized because I mean, the size of that queue is going down, right? So you're not always going to be doing order n operations. The first one you'd be order n, or order log n, then order log n minus 1, log n minus 2, et cetera, et cetera. So you might be able to get away with a little slightly fewer operations. But if we consider m to be large, n squared, what is this going to end up being? N squared log n, right? And this gets subsumed by that. Okay, so that's pretty good, right? You can further reduce this, further improvement. You can get this down to, I believe, what is it? Let me check, make sure I'm not lying. Yeah, order m plus log n, or n log n, right? So in other words, order n squared, right? Right? Yeah, plus n log n, but m again is still going to be order n squared in the worst case. So you can say that this is order n squared. In other words, you're only saving a polylog here, right? You're only getting rid of that log n. And this would involve using what's called a Fibonacci heap. Right? And we won't go into that because that's yet another data structure. But I will mention that you can get it slightly improved to n squared exactly if you just simply use a Fibonacci heap instead of a binary heap that you're familiar with, that you corrected Gomer's mistake on already. Okay? All right. Any questions on Dijkstra's presentation here as it is? Yeah.
Check Netflix, you have this character, it's dijkstra.
Dijkstra, okay. Let's settle this for once and for all. Is it French? What is it? Is it Russian? All right. I don't know why Firefox is not. All right, we're going to get lucky if this works because my OBS is slowing everything down. All right. No, I mean, you can see that the rendering here is going down because OBS is really, really working hard right now. I don't know why. How to pronounce Dijkstra. There you go. How to say Dijkstra. Dijkstra. All right, I've got my sound on.
Dijkstras.
Ah! All right, yeah, cool. That's just one person. Dijkstra.
Dijkstras.
I'm sure it's one of those those things. It depends on what region of. You said Norwegian or what? Dutch. Yeah, it depends on what region of Dutch you're from or whatever, right? All right, so that's Dijkstra or Dijkstra's algorithm. What I want to do with the remainder of our time is I want you to help me develop an algorithm that, say, given the triples from Dijkstra's, Dijkstra's algorithm, compute the actual paths, right? So let's just do it for one triple, right? So given, for example, one triple, say, yeah, we need all of the triples because we need to backtrack, but basically you have a V, you have a predecessor vertex V, a piece of V, right? And then, of course, you have the distance, which will not be necessary for us because, you know, I mean, it'll be interesting to see it, but it won't be necessary to actually build that path. All right? So let's come back over here to, I don't know, let's outline this, all right? And for that, I'll go ahead and get rid of this stuff over here, all right? I do want this visualization, though, so that we can develop this algorithm and then ultimately write pseudocode. So given, say, v, p sub v, and d sub v, right? Output the path from S to V. And that's just going to be simply a list, right? Okay? So, for example, when you develop an algorithm, usually, you know, you write out an example in order to understand how to do it. And then you generalize that example. So let's do it for I, right? Remember, I has a predecessor vertex of G at a cost of 20. Right? So initially, I'm going to say that, well, I can get to I here, but where do I come from? Right? I look at P sub I. Right? This is going to be P sub I, the predecessor vertex of I, which is equal to G. Right? That's that thing right there. But now I have a question, well, how did I get to G? Right? Then I look up the predecessor vertex for G. Right? So I got there from the predecessor vertex for G, which is equal to, in this case, D. Right? How did I get to D? I got there through the predecessor vertex for D. Well, what is that? I look it up for D, and then I look at its predecessor vertex, which is equal to E. Right? So all together, what did I do? E to D to G to I. Right? And there's the path that I output. Right? So help me out. If I've been given a particular vertex, so input will be the set of triples from deke-stras algorithm, and a vertex, say V, vertex V, right? My output is going to be the shortest path, actually, we shouldn't say short, we should just say least weighted. Oops. Least weighted path from S to V. Okay? So initially my path is going to be simply what? I end up at V. So my path will end up being V. Okay? And then of course I want my current vertex here to also be V. Because what I'm going to do is I'm going to work backwards. Right? Way too far away now. Here's my current vertex. I look up the predecessor of the current vertex. That gives me a new vertex. I continue. What's the predecessor of that vertex? So my current vertex is going to be I, then it'll be G, then it'll be D. When do I stop? When my current vertex is the source, right? So while, two more, there we go. While the current vertex is not equal to S, work backwards. Work backwards. Right? The predecessor vertex here of the current vertex, right? Well, yeah, that's all I need, right? I need to add that to P. Yeah. So P will be updated to the predecessor vertex of the current vertex plus P. Note here that I'm prepending it. Why? Because I'm working backwards, right? So here's my path that I built so far. It looks like, you know, something like this, right? And so I need to add to the front of it whatever the predecessor was. And so the predecessor, I'm prepending that to the path and updating the path. Then I need to update the current vertex to the predecessor vertex, right? And then finally, the path will end up being S plus the path and output P. There we go. That's all. Right. All you need to do is work backwards with a while loop. Right. Well, we have enough time. Do we want to simulate it maybe? I don't know. My browser is definitely... Okay, now it's a little bit better now. If we can get this to come up in any amount of time, then we can do this, and we'll save Floyd's for next time. While we're waiting for this to come up, what was in your homework? Is it partially written too, some of it? Assignments. So yeah, I'm more than happy to push it back because we've only got 2 assignments after that.
So about the assignment,
Oh, it was 7 or 8?
the upcoming due.
Okay, 8.
So there are parts of it says you have to prove something like that. Do we use like is there a standard format we should use for proofs?
Just like what?
2 or 3, I think that's one of the prove or number 3. Like
3. Usually if we say prove or disprove, disprove, right? The minimum spanning tree formed by Prim's algorithm starting at x also provides a minimum distance tree. So if you're going to disprove something, then
just give it time.
a counterexample. Exactly.
Right.
Exactly. Yep. Come on. All I want to do is some Python stuff. Come on. All right. If this isn't going to come up, then we can either skip it or... Come on. Okay, there we go. All right, so... lectures 310, and let's go with the demo. I'm not sure what's in here. Oh, that stuff that I showed you last time. I'm just going to go ahead and get rid of it because I think it's in your notes. Come on. There we go. All right, so let's codify at least this algorithm that we just wrote. We're not going to write dijkstras together, but we will write this. All right. Now, the way that we'll write this is by creating those triples. So here's deke-stras triples, right? It'll be a list of those triples that we developed already, right? So unfortunately, this is going to be boring data entry here, but you're going to help me out, right? So what we want is C, nothing, and then 0, B, E, and 5. C, nothing, and... Oh, sorry, yes, you're right, sorry, you're right. So E, none, and 0, right? What else was there? B goes to E at a cost of 5. And I'm only going to do the ones that are relevant, D, G, and I. So D goes to E at a cost of 5. G goes to D at, or came from D at a cost of 15, and I came from G at a cost of 20. All right, I won't bother doing the data entry for all the rest, but because you can do that, and we're only going to simulate it for this one that we did right here. Okay, so let's codify this and actually write this out in Python if we want to, because it's a nice little exercise. What we need is the given vertex that we want to start at. Okay, so the given start vertex will end up being E, and the end vertex will end up being I. Right? So the predecessor will be the path. Sorry, that's path. Right, the path will end up being a list, right? And how do we insert something at the beginning of a list in Python? It's not append is at the end, so we can add. No. An index? Ooh, that doesn't sound right though. Append. Okay. All right. Anyway, the current no vertex.
You can append and then flip it.
Insert, is it? Python list insert. Insert, and then you give it a thing, the index in the thing, or the thing in the index? Index, yep, index and then the object. Thank you. All right, so I'll start at the end here, And then, you know what? What I'm going to have to do is I'm going to have to go through and find the one with, is B correct there? I should have set this up if I was going to do this well. Yeah, it'll stay. It's the same. That's all correct. All right, so there's the path. There's the current vertex. While the current vertex is not equal to the start vertex, what we'll do is we'll work backwards. 14, cur, thank you, vertex. There we go. All right, and then the path will be dot add, or you said insert, at the beginning, which is always going to be index 0, and then the current vertex. There we go. And then the current vertex will be updated to, vertex again, will be updated to the predecessor of current vertex. Cur vertex. And that's the code that I'm going to have to write and be clever about. So, predecessor, what I'll do is I'll go ahead and give it deke-stras, dijkstra, and the current vertex. And what I need to do is I need to write that function. So let's write that def predecessor of these two. And all that's going to do is go iterate through deke-stras, looking for whatever the first one is equal to the current vertex, and then it returns the second one of it. So for A, B, C in deke-stras, if A is equal to the current or cur vertex, then return B. Is that right? We agreed? All right. If I find what I'm looking for here, I want its predecessor, and I return that predecessor. Okay. So there's the current vertex. Is it good? And then at the very end here, path.insert 0 start vertex. And then print path. So now if this is correct, on our very first try here, this will end up being what? E-D-G-I. Very rarely does it work on the first time, right? Python, demo. What did I say? E-D-G-I? Ah, darn it. Oh, that probably because I misspelled something. Cur. Where did I? Cur. Thank you. 22. Is that it? Oh my God. E-D-G-I. Yay, we did it. All right. And now that's because I only had this data in there, right? If I wanted the answer to all the rest, of course, I would need to put all the data in there and make sure that it actually works by testing everything. Right. We did that in only 10 minutes. Cool. Any questions on that?
5 minutes.
Oh, 5 minutes? Okay. And we looked stuff up. And we troubleshooted in 5 minutes too. Right? So there you go. That's how you can build your paths once you've got those Dijkstra triples. Right? If I were to do this with more time, I would probably not have a list of triples. Or if I did, I would probably use a map instead, or a dictionary, I guess. Right? Where the first vertex mapped to that triple. Right? So B, since we've got time, D maps to this, G maps to that. And I'd probably also go back and change them all to double quotes, because that's the style I like, I prefer. Right? There we go. And now we don't need this function at all. Right? How do I find the predecessor of this? It's going to be dijkstra of the current vertex and I will get the second one. So, is it 2? There's 1, right? So hopefully this works exactly the same. Yay. And I simplified it by eliminating one function and using a smart data structure instead. I didn't have to iterate over it to find the one that I was looking for. The one that I was looking for ended up being the key, and so I can immediately take the key and jump to the value. True, yeah. It depends on how you implement your dijkstra too, or dijkstra, right? Yeah, you can get rid of this. If you want to, we can go deke-stras is equal to, how do you do a map comprehension? Python dictionary comprehension. What's the syntax for that? Since we have plenty of time, right? It's always nice to learn something or relearn something. My dictionary, there we go. That's what I want. I want that kind of syntax. So I'm going to eliminate that first element. And I want K, V for dijkstra 1, comma, dijkstra 2 in, well, no, I want to get rid of the 0 for, no, that's not the one, that's not the syntax I want. I want the raw syntax for dictionaries. Yeah, using a conditional for something mapping to something. So I want not K, I want deke-stras of 0 mapping to the value for V in, no, for this in deke-stras, dijkstra. I can simplify this, right? A, B, C. And my key will then be A, maps to B, C. There. Is that right? Does that look right? Well, here, let's print. You can't print. Is it pretty print? Import. Is it import? Print. Pretty print. Dijkstras. Before and after. What did you say? Oh, can you? Okay. Module is not callable. It's pprint.print, I think. Otherwise, I'll go with your solution of just print the map. All right, fine. There we go. Nope. So there it is before, right? Not enough values to unpack. Expected 3, but I got 1. And why did you get 1? Expected 3, but it got 1 out of that. Yeah, how do I get the values in a map? Dot values? Dijkstra dot values?
Yeah.
Like this?
Yeah.
Or is it vowels? Yeah, okay, there we go. And then it fails down here for other reasons because I've changed the triples. But there. Ah, cool. All right, so have you ever done a dictionary comprehension before? No? So here's I mean, list comprehensions are really cool because you can do things, the basic things like this, right? That you can, zipper these things together, or you can say, for all x squared, for x in some range, right? So you can get, you can automatically get a list using the syntax. This is even cooler in my book because what you can do is you can build an entire map in a 1 line of code, right? So all I'm doing is changing one map here by iterating over the values in this dictionary, which are triples, A, B, and C. Make A into your new key, mapping to a new double, B, C, instead. Right? Giving you a brand new map with a completely different rule for mapping stuff. Right? I think it's cool. That's one of the you think stuff like this is cool until you try to do something more moderately complex, and then it all falls apart. This is something. I mean, even something like this is still within the realm of simplicity, right? So it is not a cure-all. So Python gets undue credit for doing simple stuff cool, but the moment that you're not doing something non-simple, it ain't so cool anymore. All right, we'll go ahead and move on to Floyd's algorithm next time. Yeah.
Do this in like Java or something, it would be just multiple lines, like 10 lines.
Well, in Java, modern Java, you could probably do some Lambda function to do it, but then it gets ugly real quick. Yeah. You can't do something like this. No, it probably won't be a one-liner. It'll probably be like a series of Lambda statements of some sort, right? And then streams or iterators or something like that. Yeah. But all right, let me know if we want an extension. Otherwise, we'll talk about Floyd's on Friday, because you can choose to do Floyd's or Dijkstras in your assignment.